A bridge should look as if it had been conceived on a Sunday afternoon, says architect Eric Villefrance. The Danish state built the Farø bridges from 1980 to 85. The two bridges connect the islands of Sjælland and Falster with an intermediate landing on the tiny Farø island between them. It is a fact that very few can walk on water. We need a girder to walk on. If the water to be crossed is wide, the girder needs an intermediate support or several supports. If the sea bottom is soft, the supports must have a large footing. And if the soft material is deep, the footing must have strong roots reaching down to firm layers. If more space is required for ships passing under the bridge, part of it can be suspended by cables fixed in a tower. Then some piers can be left out. If two towers are used, even more space is provided under the bridge. The design of the concrete substructure was based on a proposal by Farø Consortium, which consists of the two Danish companies Højgaard Schultz and Campsax, the French company Campion Bernard, and the West German company Polensky and Zöllner. In order to be able to work at the bottom of the sea, a cofferdam is required. Once the cofferdam is emptied of water and excavated, a concrete slab several meters thick is cast as foundation for the pier. While excavation inside the cofferdam is carried out, automatic pumps drain groundwater out of the subsoil. With deeper water, the foundation of a pier starts with the driving of steel piles. In the middle of the sound between Farø and Falster, there are water depths of up to 30 meters, and the largest piles are some 30 meters long. The piles are driven in two concentric circles, so only a few meters remain above the bottom. Then a concrete caisson is placed, and inside the caisson, concrete is poured under water, filling the lower part of the caisson. On top of the concrete caisson, a huge steel cofferdam is fixed, and the water is drained out of the cofferdam. The foundation piles are made of steel tubes welded together to the different pile lengths required. High-quality welding is essential. All welds are checked with X-rays and ultrasonic tests. The piles shall carry loads of up to 800 tons. Each pile is made not only for a particular pier, but also for a particular position within that pier. The lower pile end is closed with a steel plate and a 3-meter-long concrete plug. The pile cannot stand driving directly on the top. Therefore, a strong dolly is inserted in the pile, and driving is performed on top of the dolly. Driving is carried out with a 6-ton diesel hammer. By counting the number of blows used on 20-centimeter penetration, the pile's load-bearing capacity is registered continuously. Skillful design has enabled Farø Consortia to achieve an unusually high load-bearing capacity for the piles and outstanding precision in placing them. The concrete caissons are prefabricated on the site. The largest caissons weigh 450 tons and are sailed out to the pier sites by a floating crane with a lifting capacity of 600 tons. The construction methods applied by Farø Consortia would not be possible without the heavy equipment and sophisticated measuring devices. 15 out of the total number of 36 piers are founded on piles, using concrete caissons. Once the caisson is placed, the underwater concrete around the piles is cast. The method applied is used here for the first time at such great depths. It is based on a special valve at the end of the concrete casting pipe, permitting the pipe to be moved without risk of exposing the fresh concrete to the sea. Everything is a bit more complicated than indicated in the model, but soon solid concrete floors are routinely produced 30 meters below water level. Then again, it is the gigantic floating crane's turn. On top of the concrete caisson, a steel cofferdam is fixed. The joint between concrete caisson and steel cofferdam is made watertight by using a heavy rubber gasket. Now the cofferdam is emptied of water. In the bottom of the cofferdam is now cast a thick reinforced concrete slab, covering the protruding steel piles completely. The pier shafts are solid up to 2 meters above sea level, whilst the remainder is hollow. All 45,000 cubic meters of concrete used in the substructure of the bridges are produced at the mixing plant erected by the consortium at Farø. Concrete materials are selected in order to meet the very demanding requirements. Fly ash is added to the concrete in order to improve the workability and to reduce bleeding. Much effort has been used in devising efficient transport of concrete. This vessel started its life as a landing craft. Before concreting can start, the steel reinforcement shall be placed, checked, and approved. After approval, the pouring of concrete is begun. Samples are taken of each concrete batch for testing. The results of these tests serve to ensure that the prescribed quality of the concrete is maintained. The solid pier top distributes the loads from the superstructure to the pier walls. When construction work has reached its maximum intensity, Farø Consortia employs around 150 workers. In spite of the nature of the works and the large number of employees, no serious accidents occurred during the construction period. The piers closest to the Sjælland coast are just over 20 meters high. From here, the bridge descends towards Farø in a soft curve, landing on this island a few meters above sea level. After 3 years of work, the piers for the northern bridge are ready to receive the first section of the superstructure. The other bridge, the one between Farø and Falster, is more complicated. Monbear and Torsen won the contest for the superstructure with a novel steel box girder designed by Consult. The girders for the two bridges were built at Højgaard shipyard as 12-meter-long boxes. Adjacent to the shipyard, the contractor had established an area where the box elements were welded together to form 80-meter-long bridge spans before being transported to the bridge site. The box elements are pulled up to each other and their ends held in position. To weld together box elements of this type is no easy undertaking. It is not merely the outer plate edges which have to be joined. The final pieces of the trough sections, which provide the longitudinal stiffening of the box girder, must be inserted and welded. The welds are submitted to a very stringent quality control, and a Consult supervision team is inspecting the fabrication. There is a manhole in the middle of each bulkhead, giving access from one end of the bridge to the other. The dimensions of the bridge are calculated very precisely, and if one made a scale model of this size, it would have to be made of ultra-thin paper. Here are 80-meter lengths of motorway lying side by side, waiting to be transported to the bridge site. Before transportation to the site, each section passes through the paint station. The durability of the bridge is dependent on how well the steel is protected against corrosion. Therefore, the first coat of paint is not applied until the plates have been cleaned right down to the bare steel. The middle part of the Farø-Falster bridge is supported by cable stays, which pass through tubes in the box girder. In order to give room for these, the bridge is slightly wider than the Farø-Sjælland bridge. But how are the cable stays anchored above? From the piled foundation and up to the water level, the two bridge towers are constructed as all the other pile-founded piers. But from this point, the tower splits into two hollow legs. The towers are cast in reinforced concrete by Farø Consortiet as part of the substructure contract. The bridge deck does not rest on the crossbeam of the tower. It is suspended by the stay cables. The tower rises to a height of 96 meters. The most difficult of all concrete pours is the one just above the water. The steel reinforcement is so tight that it is difficult to insert the vibrator needles in the concrete. When the concrete starts curing, its temperature increases, and the difference between the temperature of the cold old concrete and the warm new concrete can create dangerous tensions. The Farø Consortium chooses to cool the fresh concrete with liquid nitrogen. As the tower legs grow, the cranes, lifts, etc. gradually increase in height. One particular problem was the construction of the complicated steel boxes, which Farø Consortiet shall fit into the top of the tower as fixing points for the cable stays which will eventually carry the navigation spans. The box is now ready to be lifted into place. The stay cables shall later be inserted in holes in the box. When the box is in place at the top of the tower, it is embedded in reinforced concrete. The bridge shall be completed in June 1985. There are still 1.5 years left, but nevertheless no time to lose. The box has to go up, regardless of frost, wind or snow. In the finished tower top, the box is now enclosed with the height of a 3-story building. Heavy anchor bolts tie the 2 legs together around it. And now all is ready for the steel box girder. A distinctive vessel arrives at Nakskov to fetch the first bridge span and take it to Farø. The box weighs 600 tons and is hanging ready from the gantry crane. The basic idea is simple. Boxes are built on an assembly line at one place, and about 100 kilometers away, a row of piers stands ready to receive them. In order to transport the boxes, one must use a ship which does not capsize easily, a catamaran. The boxes are lifted up to the height of the bridge piers, all ready before transport. At the bridge site, one simply sails in between the piers and puts down the boxes in their proper positions. And so the first 80 meters of motorway come sailing over the sea. Between the piers on land, an elevated launching track is built. The catamaran goes in between 2 piers standing in the water and sets the box down on them. When the catamaran has left again, a pontoon, also with an elevated track, is towed in beneath the box. Lastly, a sledge is brought out to carry the box towards the abutment. Here the catamaran with the first box has mooring ropes out on all sides and is pulling itself carefully into position. The sledge has stainless steel sheets sliding on Teflon bearings. Some hours later, the box is already halfway onto the track above land. And so came box after box to be welded together to form one continuous bridge girder. During the erection and welding of the box girders, adjustments had to be made to compensate for the dead load deflections, so that a level bridge could result. The heat from the sun can cause the upper surface of a box to expand more than its lower surface, thus giving an upwards curve. It is necessary for long periods during the summer to cool the bridge with sprinklers. It was a hard task to get the first box into position, but by the 4th and 5th boxes the erection time has been cut by half. However, new challenges are to come. The middle part of the Farø Bridge is supported by cable stays. Only one end of box number 38 rests on a pier, while box number 39 floats freely between the two legs of the tower. Therefore, a temporary support has to be provided. An enormous structure was attached to the tower and supported right down upon the foundation. Box number 38 was placed with one end on this structure and the other end on the bridge pier. Now it is the turn of box number 39. This time the catamaran has, in addition, a launching track mounted on top. The catamaran is eased gently into position using the mooring ropes. The box is then pulled through the tower.
Du kan sigte ind på doren, ikke? Og så ligger 50 cm over doren, så begynder vi på ind med den, ikke? Men du må godt have den skubbet helt ud og langs. Og så
Mounted on the bridge tower is a giant clamp with a pin, and on the catamaran is an eye plate which fits down over the pin and holds the catamaran firmly in position. Later, a hydraulic support system is installed between the tower legs and the box girder to prevent twisting of the bridge deck. The box can only tolerate minor deformations, which means that the catamaran has to lie very still and precisely before one can begin to pull the box.
Peter, 10 tons. 10 tons, ja. 158. Den kører med minus. Er det okay? Ja, den kører på vej. Mere, der er en 20 mm ned, ja.
As the box slides in, the catamaran lightens. However, compensation for the movement upwards is made by means of jacks and ballast. And now the cable stays are missing. The last catamaran transported box first has to be hung from 4 stays 16 meters apart. Each stay consists of parallel 7 mm steel wires in a polyethylene tube. The wires are cast into the socket using epoxy containing small steel balls. The working space in the tower top anchorage is about as big as a 3-story telephone booth. The cable stays are stiff. The tubes cannot tolerate sharp bends.
Ja, stop. Jeg skal ikke køre længere.
An extension rod is inserted from below and screwed into the end of the stay socket. A jack is applied to the lower end of the extension rod and the stay is pulled downwards to be anchored to the bridge. From here to the center, the bridge girder is built up from smaller boxes, 16 meters long. They are brought on a barge 2 at a time. In order to provide room for the final section, 1/2 of the bridge is pulled 10 centimeters in towards land. When the bridge has been pulled back into position again, there is just enough room for the 2 welding seams. The painters work from a suspended platform. The boxes receive their first coats of paint at Nakskov, but the final coat is applied here. The inside of the steel box girder has 4/5 of the area to be protected against corrosion. So here, saving the painting, a dehumidification plant is installed. This sends a stream of dry air through the bridge girder and keeps it completely free from corrosion. The roadway's asphalt must both protect the steel and provide a good wearing surface. The bottom layer is applied under cover of a tent, enabling temperature and humidity to be controlled. The crash barrier and an emergency footpath are constructed in one piece as 8-meter-long elements. Finally, a steel railing is put up. Each of the 2 bridges is in fact just one long beam, fixed only in the middle. On the remaining piers are bearings, on which the beam can slide up to 1/2 meter backwards and forwards, according to temperature variations. The bridge movements are absorbed by the abutment expansion joints, made up from steel beams with rubber seals. On the appointed day, the Farø bridges are opened by Her Majesty the Queen of Denmark, Margrethe II. A bridge should look as if it had been conceived on a Sunday afternoon.